A planet's destiny is written in its air. We often think a world is defined by its rock and its place in orbit, but the real story unfolds in the thin, fragile blanket of gas wrapped around it. This video will give you a complete framework for understanding how atmospheres act as the ultimate architects of alien worlds, turning dead rocks into potential cradles for life. How can a planet just like Earth become a scorching hellscape while a frozen moon develops rivers and rain? The answer lies in the invisible forces at work within a planet's sky. What do you think makes our own blue sky so extraordinary? That blue sky is a planetary superpower. For decades, astronomers searching for other Earths have focused on a single, simple rule. They call it the circumstellar habitable zone, or more poetically, the Goldilocks zone. It's that narrow band around a star where temperatures are just right, not too hot and not too cold, for liquid water to pool on a planet's surface. Find a rocky world orbiting within this zone, the thinking goes, and you might just find a second home for life. But this classic idea has a critical flaw. It assumes every planet is naked, it forgets the atmosphere, and that single oversight turns the entire search for habitable worlds on its head. Take our own solar system as a case study. Venus orbits just inside the inner edge of the Sun's habitable zone. By the simple distance rule, it should be a slightly warmer, steamy version of Earth. Instead, its surface is hot enough to melt lead, crushed under an atmosphere 90 times thicker than our own. Mars, on the other hand, sits comfortably within a broader definition of the zone. Billions of years ago, it had rivers and lakes. Today, it's a frozen, barren desert because its atmosphere became too thin to hold onto heat and water. Both worlds share an orbit that, in theory, could support life, yet one is an oven and the other an icebox. The difference wasn't written in their orbits. It was written in their skies. This reveals a profound truth. A planet's atmosphere doesn't just exist within the habitable zone, it actively defines it. A thick, insulating blanket of greenhouse gases can push the zone's inner edge much closer to the star, warming a world that would otherwise be frozen. Conversely, a world with no atmosphere or one that has been stripped away finds the habitable zone shrinking away from it, no matter how perfectly it's placed. The zone isn't a fixed ring of real estate around a star. It's a dynamic, shifting space whose boundaries are drawn by the chemistry and physics of a planet's air. So if distance from the star is only the opening chapter of the story, what are the actual properties of an atmosphere that determine whether a world lives or dies? The key to a world's warmth is not just its distance from the fire, it's the blanket it wraps around itself. An atmosphere acts as a planetary thermal blanket, and the mechanism that makes it work is one of the most important ideas in planetary science, the greenhouse effect. At its heart, this is a simple, neutral process of physics. Sunlight, which is mostly visible light, passes through a planet's atmosphere and warms the ground. That warm ground then radiates heat back upward, but this energy is now in the form of invisible infrared radiation. Certain gases in the air, like carbon dioxide, water vapor, and methane, are transparent to visible light but opaque to this infrared glow. They absorb that outgoing heat and re-radiate it in all directions, sending a portion back down to the surface. This recycling of energy is what raises a planet's temperature above what it would be if it were just a bare rock under the sun. Without any greenhouse effect at all, Earth's average surface temperature would be a frigid negative 18 degrees Celsius, a globally frozen ball where all water would be permanent ice. Our planet's moderate, natural greenhouse effect, primarily from water vapor and carbon dioxide, provides a crucial 33-degree boost. That is the difference between a snowball and a world of blue oceans, of rivers and rain. It is the reason we have liquid water at all. Now look at the two bookends in our own solar system. Mars possesses an atmosphere only about 1% as thick as Earth's. It has trace amounts of greenhouse gases, but they are so sparse they cannot trap heat effectively. The little warmth Mars gets from the sun simply radiates straight back out into space, leaving the surface brutally cold. Venus tells the opposite cautionary tale. It has an atmosphere choked with carbon dioxide, creating a greenhouse effect so intense and runaway that the surface bakes at 460 degrees Celsius. The same physical process that gives Earth its gentle warmth created an unlivable oven on Venus. This stark contrast reveals the critical truth. The greenhouse effect itself is not good or bad, it is simply a tool. A world's fate is decided by the type and, more importantly, the amount of greenhouse gases in its atmospheric blanket. A little gives you a temperate world. Too little leaves you in a deep freeze, too much, and you forge a hellscape. So if the greenhouse effect sets the thermostat, what force decides how thick that atmospheric blanket is in the first place? What determines whether a planet holds onto a life-giving shroud or loses it to the void of space? The thickness of an atmosphere does more than just trap heat, it creates an entire physical environment. This brings us to a second, equally vital property: atmospheric pressure. You can think of pressure as the weight of the sky pressing down on everything at the surface. On Earth, at sea level, that weight is substantial, and it plays a hidden but essential role in one of the most fundamental requirements for life as we know it: liquid water. Water is a fussy substance. It can exist in three phases: solid ice, liquid water, and gaseous vapor. Whether it settles as a liquid depends on a delicate balance between temperature and the pressure pushing down upon it. Scientists refer to a special set of conditions called the triple point, the precise temperature and pressure where ice, liquid water, and water vapor can all coexist in perfect equilibrium. For water, that point is 0.01 degrees Celsius at a pressure about 160 times thinner than Earth sea level air. Here is the crucial part. If the atmospheric pressure is below that triple point value, liquid water becomes fundamentally unstable. On a cold day, any water will simply stay frozen as ice. On a warm day, it won't melt into a liquid, it will sublimate, turning directly from ice into vapor and vanishing into the air. This is the stark reality on the surface of Mars today. The Martian atmosphere is so incredibly thin that its surface pressure is far below water's triple point. If you were to take an ice cube from one of its polar caps and place it in the midday sun at the equator, it would not form a puddle. It would fizz and disappear into the thin air as gas, a process we never witness under our own thick sky. This explains why, despite tantalizing evidence of occasional, salty brines that might briefly darken Martian slopes, persistent liquid water cannot exist openly on its surface. The pressure is simply too low to allow a river or a lake to form. Our planet, with its robust atmospheric pressure, exists comfortably above this threshold. This pressure literally holds water in its liquid form, allowing our oceans to remain oceans, our rivers to flow, and raindrops to fall. It creates the stable medium in which chemistry can unfold over vast stretches of time. And this principle extends beyond water. If life elsewhere were to use a different liquid solvent, like methane on a cold moon, that solvent would also have its own triple point, its own required pressure to exist as a liquid sea. So atmospheric pressure acts as a planetary bottle cap, determining which liquids can pool on the surface and for how long. But this raises a deeper puzzle. If pressure is so vital, where does it come from in the first place? What gives a planet its atmospheric weight, and more importantly, what forces can take that weight away? A planetary atmosphere is also a shield, the first line of defense against a universe that is far from friendly. Beyond setting the temperature and pressure, this layer of gas performs a vital protective function, filtering out dangers that would otherwise make the surface sterile. The first of these threats comes from the star itself, a constant barrage of high-energy ultraviolet radiation. On a world without protection, this UV light acts like a powerful disinfectant, breaking apart the complex organic molecules that are the building blocks of life. Earth's solution is a specific layer within its atmosphere, the ozone layer. Ozone is a molecule made of 3 oxygen atoms, and it forms naturally when sunlight interacts with the oxygen in our air. This thin, diffuse band high in the sky acts like a planetary sunscreen, absorbing the most harmful ultraviolet rays before they can reach the ground. It is not a perfect barrier, but it is a critical one. Other worlds might develop different photochemical hazes that serve a similar purpose, a smog of protective compounds created by the interplay of starlight and atmospheric chemistry. Without such a filter, life would be forced to hide deep underground or underwater, severely limiting its chances to flourish and diversify on land. The second protective service is more dramatic, a nightly light show that demonstrates the atmosphere in action. Our sky is constantly peppered with dust and rock, remnants from the formation of the solar system. When these particles, called meteoroids, enter the atmosphere at tremendous speeds, they collide with air molecules. This friction generates intense heat, causing the vast majority of them to vaporize in a brilliant streak of light, a meteor or shooting star. This process acts as a global defense system, incinerating countless potential impactors that would otherwise rain down on the surface. Imagine a world with little to no atmosphere like our moon. Its scarred, cratered face is a direct testament to this lack of protection, bearing the marks of every single impact, large and small, over billions of years. An atmosphere of sufficient density provides a natural buffer, ensuring that only the largest and most robust objects can make it to the surface intact, turning a constant bombardment into rare and extraordinary events. Perhaps the most invisible yet crucial shield involves a planet's magnetic personality. Our Earth is not just a ball of rock, it is a dynamic dynamo with a molten, metallic core that churns and spins. This motion generates a powerful magnetic field that extends far out into space, creating an invisible structure called the magnetosphere. This magnetic bubble does 2 essential things. First, it deflects the solar wind, a relentless stream of charged particles constantly blowing from the sun. Second, it traps some of these particles in vast, donut-shaped zones around the planet, the Van Allen radiation belts. This complex interaction prevents the solar wind from directly stripping away our atmosphere over time, a fate that likely befell Mars when its internal dynamo ceased. The magnetosphere and the upper atmosphere work in tandem, with magnetic forces channeling energetic particles toward the poles, where they interact with gases to create the shimmering auroras. So while the magnetic field is born from a planet's interior, its protective power is realized through its interaction with the sky. Without these combined defenses, a world's surface would be exposed to mutagenic radiation, relentless micrometeorite erosion, and the slow, suffocating loss of its very air. The atmosphere, therefore, is not a passive blanket, it is an active guardian, but this brings us to a final, profound question. If an atmosphere is so vital for warmth, pressure, and protection, where does it come from in the first place? And what mysterious forces can steal it away from a world, leaving it silent and exposed under the stars? The chemical recipe of an air determines what kind of world can breathe beneath it. We often think an atmosphere is defined by what it contains, but its true power lies in what it allows. Our own sky, a mix of roughly 4 parts nitrogen to 1 part oxygen, feels normal and inevitable. Yet this specific blend is not a universal standard, it is a profound anomaly, a signature written by life itself. For most of Earth's history, our air was utterly alien to us, a toxic fog of carbon dioxide, methane, and ammonia with virtually no free oxygen. The rise of photosynthetic microbes, tiny organisms that could harness sunlight, began a planetary-scale chemical revolution. They released oxygen as a waste product, a gas so reactive it was a poison to most early life. This great oxidation event transformed the planet, rusting the oceans and continents, driving many ancient life forms to extinction, but ultimately paving the way for complex, oxygen-breathing organisms like us. Our breathable air is not a starting condition. It is the exhaust of a global biological engine that has been running for billions of years. This reveals a critical insight for searching other worlds. The presence of large amounts of free oxygen in an atmosphere is a massive red flag, a state of extreme chemical tension. Oxygen is a voracious element. It wants to bind with rocks, with iron, with carbon, and disappear. To have it accumulate in an atmosphere requires a powerful, continuous source replenishing it against this constant drain. On Earth, that source is life. So if we were to spot significant oxygen in the air of a distant exoplanet, it would be one of the strongest potential biomarkers we could detect, a hint that something on that world is constantly pumping that reactive gas into the sky. But oxygen is not the only clue. Methane is another. In an oxygen-rich atmosphere like ours, methane should be quickly destroyed by chemical reactions. Finding both gases together in stable amounts is like seeing a fireplace that never runs out of logs while the room fills with smoke. It suggests something is actively adding fuel to the system, possibly biological processes. Yet the active ingredients like oxygen or methane are only part of the story. The true stabilizing backbone of many atmospheres is something far less reactive, the buffer gas. On Earth, that role is played by nitrogen. Nitrogen is largely inert. It does not easily engage in chemical reactions under normal conditions. This makes it the perfect diluent, the background actor that prevents the more reactive players from causing runaway chaos. It provides the bulk of the atmospheric pressure that holds our water liquid without itself participating in the intense greenhouse effect or the fire of respiration. A world without a stable buffer gas might see its atmosphere swing violently between different chemical states, making long-term climate stability, and thus long-term habitability, nearly impossible. We must also consider the spectrum of atmospheric chemistry beyond our own experience. A reducing atmosphere, rich in gases like methane, hydrogen, and ammonia, is one where chemical reactions tend to add electrons. This was the primordial soup of early Earth, and such an environment can be favorable for the formation of the complex organic molecules that lead to life. However, it is also often opaque, trapping heat efficiently and potentially shrouding a world in a thick, orange photochemical haze. An oxidizing atmosphere, dominated by oxygen or other electron-hungry compounds, is great for high-energy processes like animal metabolism, but is highly corrosive and flammable. Each type sets a different stage, favoring different kinds of chemistry and potentially different pathways for biology. And then there is carbon dioxide, the versatile workhorse. It is the essential greenhouse gas that keeps worlds from freezing, a building block for the sugars of photosynthesis, and a key component in the planetary carbon cycle that regulates climate over eons. Its presence alone does not indicate life, but its abundance and relationship to other gases can tell a deep story about a world's volcanic activity, its oceans, and whether its surface processes are in balance. The composition of an atmosphere is therefore a complex language. It speaks of a world's geology, its history of bombardment and outgassing, and most tantalizingly, it may whisper the faint chemical signature of a biosphere. But if the air itself can be a message, how do we begin to read it from light years away? What tools let us taste the breath of a distant world? The air is not a static shroud, it is a dynamic, breathing system. A truly habitable world requires more than just the right ingredients today. It demands a remarkable stability over millions, even billions of years. Our own Earth has avoided the fate of its neighbors not by chance, but because its atmosphere is part of a vast, self-regulating machine. This machine prevents wild swings between a global icehouse and a scorching hothouse, maintaining the gentle conditions life needs to evolve. The secret to this stability lies in a concept called negative feedback loops, processes that automatically correct for change and keep the planetary system in balance. The most powerful of these is Earth's geological thermostat, the Carbonate-Silicate Cycle. It works like this. Carbon dioxide in the air dissolves in rainwater, forming a weak acid. This acidic rain slowly weathers continental rocks, breaking them down. The weathered minerals, along with the carbon, are carried by rivers to the oceans. There, tiny marine organisms use that carbon to build their shells and skeletons from calcium carbonate. When these creatures die, their shells sink to the ocean floor, eventually getting buried and compressed into limestone rock, locking the carbon away for millions of years. This process steadily draws carbon dioxide out of the atmosphere, cooling the planet. But here is the clever part. If the planet gets too cold, global glaciation slows down rainfall and rock weathering. Volcanic activity, which constantly pumps carbon dioxide from Earth's interior into the air, continues unabated. With the weathering sink turned down, carbon dioxide builds up again, the greenhouse effect strengthens, and the planet warms back up. This cycle operates with the patient rhythm of geology, taking hundreds of thousands of years to complete a single turn, yet it has reliably prevented Earth from permanently freezing or boiling over. But not all feedbacks are stabilizing. Some are positive, amplifying any initial change and pushing a climate toward an extreme. The ice-albedo feedback is a classic example. Albedo simply means reflectivity. Bright, white ice and snow reflect most sunlight back into space, while dark ocean water or land absorbs it. If a planet cools slightly and ice caps grow, the increased reflectivity causes the planet to absorb even less solar energy, leading to more cooling and more ice growth. This is a powerful, self-reinforcing loop that can plunge a world into a deep global ice age. Conversely, if warming melts ice, the darker surfaces exposed absorb more heat, causing more warming and more melting. This same type of amplifying logic can trigger a catastrophe in the opposite direction. On a world with abundant surface water, rising temperatures increase evaporation, putting more water vapor, a potent greenhouse gas, into the air. This causes more warming, which leads to even more evaporation. If this cycle runs unchecked, it can spiral into a runaway greenhouse effect, where the oceans literally boil away into the sky, leaving a permanent, scorching haze. This is the terrifying fate we believe befell Venus. The difference between a stable world like Earth and an unstable one is the balance of these forces. Stability is not a default setting, it is an active, hard-won achievement. It requires the right combination of geology, liquid water, and atmospheric composition to set those crucial negative feedbacks in motion. A world without active plate tectonics to recycle carbon, or without large oceans to facilitate the cycle, may lack this built-in thermostat entirely. Its climate could be at the mercy of every volcanic eruption or asteroid impact, swinging violently between states. The long-term calm of our own sky is the result of a planetary-scale conversation between rock, water, and air, a conversation that has whispered the conditions for life's grand story. Yet, if a world's atmosphere is this complex and delicate, how do we begin to detect its subtle signatures from unimaginable distances? The stability of an atmosphere is only the beginning. To truly shape a world, that air must be in constant motion. A planet's sky is a restless engine, a global conveyor belt that performs one of the most vital tasks of all, redistributing energy. Without this ceaseless circulation, our Earth would be a planet of unbearable extremes, with equatorial regions broiling under relentless sun and the poles locked in permanent dark ice. The movement of air and water moderates these differences, stitching together a single, interconnected climate system from what would otherwise be isolated and hostile zones. This grand choreography begins with a simple fact: the sun heats the equator far more intensely than the poles. Hot air at the equator rises, creating a band of low pressure. This air then travels high in the atmosphere toward the cooler poles, but it does not make the journey in a single, smooth arc. The planet's rotation intervenes, bending these flows into the great wind belts we recognize from weather maps. Scientists describe this pattern with 3 broad circulating cells in each hemisphere. Nearest the equator, the Hadley cell is the most powerful. Warm, moist air rises near the equator, cools at high altitude, and drops its moisture as torrential tropical rains. The now dry air then sinks back down around latitudes 30 degrees north and south, creating the world's great subtropical deserts like the Sahara. The polar cell operates on a smaller scale near the poles, with cold, dense air sinking and flowing outward. Sandwiched between them, the feral cell is driven more by the interaction of its neighbors than by direct heating, and it gives us the prevailing westerly winds that dominate the weather in temperate latitudes like North America and Europe. These cells are not just abstract ideas, they are the architects of our lived experience. They dictate where rainforests flourish, where deserts lie barren, and where storm tracks migrate with the seasons. But this atmospheric engine does not work alone. It is intimately coupled with a second, slower, and more massive system, the oceans. Ocean currents, driven by winds, salinity, and temperature differences, act as planetary heat batteries and delivery trucks. The Gulf Stream, for instance, carries warm tropical waters across the Atlantic, giving Western Europe a climate far milder than other regions at the same latitude. This ocean-atmosphere partnership creates phenomena like the El Niño Southern Oscillation, where shifts in Pacific Ocean temperatures alter rainfall patterns and storm intensity across the globe. The air and the sea are in a constant, whispering dialogue, trading heat, moisture, and momentum, and this complex partnership is what makes Earth's climate both richly varied and remarkably resilient. Now consider a world where this circulation faces its ultimate test, a tidally locked exoplanet. Many of the rocky worlds we have found in the habitable zones of red dwarf stars are likely locked by gravity, with one hemisphere in permanent, blistering daylight and the other in endless frozen night. On such a world, the concept of a temperate zone defined by latitude breaks down completely. The habitable region would not be a band circling the globe, but a thin, precarious ring at the border between eternal day and eternal night. For life to have a chance there, the atmosphere must become a heroic heat transport system. A thick, global blanket of air would be absolutely essential. Powerful, planet-spanning winds would have to rage continuously, carrying scorching heat from the dayside toward the frigid night side, while cooler air flowed back underneath. This relentless circulation could, in theory, prevent the atmosphere on the night side from freezing solid and collapsing onto the surface, and prevent the day side from overheating into a permanent inferno. The result might be a world where the terminator line, the border between light and dark, is not a sharp edge but a wide, turbulent twilight ring of moderate temperatures, where liquid water could exist and clouds might perpetually gather. On such a planet, you would not have a sunrise or sunset. You would have a permanent, howling storm at the edge of light, a tempest sustained by the desperate need to balance a star's uneven gaze. This reveals a profound principle. The circulation of an atmosphere does not just moderate a climate, it can actively create a habitable environment where one should not exist at all. Gravity is the ultimate gatekeeper for a world's sky, Before any of the beautiful complexity of climate or chemistry can even begin, a planet must pass a brutal physical test. It must be massive enough to hold onto its atmosphere against the relentless pull of the void. This fundamental requirement comes down to a simple race between two forces: the planet's gravitational grip and the speed of the gas molecules in its air. Every particle in an atmosphere is in constant, frantic motion, buzzing with heat energy. For a planet to keep its air, its gravity must be strong enough that the escape velocity, the speed needed to break free from its pull entirely, is higher than the average speed of those gas molecules. If the molecules are too fast or the planet's grip too weak, the atmosphere will simply evaporate into space over time, molecule by molecule. This slow, steady leak is known as thermal escape or Jean's escape. It's why some worlds are born with air but die in silence. Look at the stark examples in our own celestial neighborhood. Mercury, the innermost planet, is not just hot, it is small. With only about 5% of Earth's mass, its gravity is too feeble to hold onto anything more than the faintest whisper of an exosphere, a scattering of atoms so thin they barely count as an atmosphere at all. Our own moon suffers the same fate. Any gases released from its interior or delivered by comets over the eons have long since drifted away, leaving its surface exposed and stark under the sun. Now contrast them with Earth and Venus. Both are worlds of substantial mass, with gravity powerful enough to retain thick, complex atmospheres across billions of years. Their size gave them the foundational strength to build and maintain the blankets that define them. But gravity is not the only thief. A planet's star can be an active accomplice in atmospheric loss, especially in the turbulent youth of a solar system. Young stars are often unruly and violent, emitting intense bursts of ultraviolet radiation and unleashing a ferocious solar wind, a stream of charged particles that blows outward at millions of kilometers per hour. These forces do not just gently heat the air, they can attack it directly. High-energy UV light can break apart molecules in the upper atmosphere, and the solar wind can then sweep those lighter fragments away, carrying them off into the void. This process, known as non-thermal escape, can strip a world bare even if it has the gravity to hold a calm atmosphere. Many scientists believe this is a key part of the story of Mars. While smaller than Earth, Mars is still large enough that, in a gentler stellar environment, it might have held onto a much thicker atmosphere. But evidence suggests that in its first billion years, our Sun was a far more active and aggressive star. Combined with the loss of its protective global magnetic field, Mars may have had its early, potentially life-friendly atmosphere slowly but surely scoured away by this relentless stellar weather, leaving behind the thin, cold shell we see today. So a world's ability to keep its sky is a precarious balance. It needs the bulk to have a strong gravitational hand, and often it needs an additional shield, like a magnetic field, or the fortune of orbiting a quieter, mature star. Without this combination, even a world placed perfectly in the habitable zone is just a naked rock, its potential for life stolen before the story could truly begin. But if size and stellar environment set the stage, what happens next? How does a planet that passes these initial tests actually acquire its atmosphere in the first place? Where does the raw material for an entire sky come from? Venus stands as our solar system's most profound warning, a world almost exactly Earth's twin in size and mass, orbiting just inside the habitable zone's inner edge, should have been a sister planet. Instead, it is a monument to atmospheric catastrophe. Early in its history, Venus likely possessed vast, shallow oceans, a gift from the same water-rich comets and asteroids that filled our own seas. For a brief, hopeful epoch, it may have been a wet, rocky world not unlike our own, but something went terribly wrong, and the atmosphere became the instrument of its ruin. The leading suspect is the slow, steady brightening of our Sun. As stars like ours age, their luminosity increases, On Venus, this incremental warming may have pushed the planet past a critical threshold. Evaporation from its oceans began to outpace rainfall. More water vapor, a potent greenhouse gas, entered the air, trapping more heat, which caused even more evaporation. This created a positive feedback loop with no natural break. Unlike Earth, Venus may have lacked the geological machinery to save itself. Our planet's Carbonate-Silicate Cycle acts as a long-term thermostat, pulling carbon dioxide out of the air and locking it in rock. Venus, with its likely stagnant, single-plate crust and no global oceans to facilitate the cycle, had no such release valve. Volcanic activity continued to vent carbon dioxide into the thickening, steamy atmosphere, but there was no weathering process to remove it. The planet was trapped in a chemical prison of its own making. The runaway greenhouse effect took hold with terrifying finality. Temperatures soared until the oceans themselves began to boil, their water vapor rising into the upper atmosphere. There, intense solar radiation broke the water molecules apart, allowing the lightweight hydrogen to escape into space forever. The oxygen was left behind to bond with rocks and carbon. What remained was an atmosphere transformed into a crushing, toxic blanket. Today, the air of Venus is almost pure carbon dioxide, 90 times denser than Earth's. The surface pressure is equivalent to being nearly a kilometer deep in one of our oceans. This immense blanket sustains a surface temperature of 460 degrees Celsius, hot enough to melt lead and zinc. High above, the clouds are not made of water, but of corrosive sulfuric acid, reflecting sunlight and completing the planet's hellish portrait. Venus teaches us that an atmosphere is not a passive environment. It is an active, dynamic force that can utterly dominate a world's destiny. The same greenhouse effect that gives Earth its gentle warmth, left unchecked by stabilizing cycles, can become an engine of absolute sterilization. It shows that location within a star's habitable zone is merely a suggestion, a starting point. The true verdict on a world's fate is delivered by the complex, and sometimes fragile, conversation between its air, its water, and its rock. Mars tells a different, quieter story of loss. While Venus transformed its atmosphere into a weapon, Mars suffered the opposite fate. Its life-giving blanket slowly stripped away until the world fell silent. The evidence for its dramatic past is written across its rusty surface, a landscape of ghosts. From orbit, we see unmistakable dry river valleys, vast networks of channels that branch and converge like veins on a leaf. We have mapped the outlines of ancient lake beds and even the faint, salty residue of what may have been a northern ocean. These are not the features of the cold, bone-dry desert we see today. They are the indelible scars of a warmer, wetter youth, a time over 3 billion years ago when rain fell, rivers carved canyons, and liquid water pooled on the Martian surface. For that to have been possible, Mars must have possessed a much thicker atmosphere, one with a robust greenhouse effect to raise temperatures above freezing and sufficient pressure to keep water from instantly boiling away into the thin air. So what happened to that sky? The culprits are a combination of planetary scale and internal decay. First, Mars is small, only about half Earth's diameter and just over a tenth of its mass. This lower gravity meant its grip on its atmosphere was always more tenuous. Lighter gases, especially the hydrogen from broken water molecules, could escape more easily over time through thermal escape. But the decisive blow likely came from within. Planetary scientists believe early Mars had a molten, churning metallic core that generated a global magnetic field, much like Earth's does today. This magnetic bubble would have deflected the charged particles of the solar wind, shielding the atmosphere from direct erosion. Then, something critical changed. The smaller planet cooled faster than Earth. Its core likely solidified or its internal dynamo ceased to churn. The protective magnetic field collapsed, leaving the atmosphere utterly exposed. With the shield gone, the solar wind, a relentless stream of charged particles from the sun, began to directly scour the upper atmosphere. Ion by ion, molecule by molecule, the solar wind could strip the air away, a process called sputtering. NASA MAVEN orbiter has measured this ongoing loss in real time, observing how solar storms dramatically increase the rate at which Mars's remaining atmosphere is still being peeled back into space. The result is the world we see now. The once thick blanket is gone, leaving behind a wispy remnant less than 1% as dense as Earth's. It is composed almost entirely of carbon dioxide, but it is far too thin to trap any meaningful heat or create sufficient pressure. On the Martian surface today, the atmospheric pressure is below the triple point of water. This means a cube of ice placed in the sun does not melt into a puddle. It sublimates, vanishing directly into vapor. Any liquid water that might briefly emerge from underground would either freeze instantly or boil away in the near vacuum. The transformative blanket that once carved valleys and filled lakes has been reduced to a faint, cold shroud, incapable of sustaining the processes that once made Mars a candidate for life. This world did not become inhospitable because its atmosphere turned hostile, but because it was lost to the void. Mars stands as a solemn counterpoint to Venus, demonstrating that a planet can be rendered ordinary, frozen in time, not by an excess of its sky, but by its heartbreaking absence. Yet our solar system holds a world that shatters every expectation. Far beyond the inner planets, in the frigid depths of the Saturnian system, a moon cloaked in an orange haze presents a vision of alien habitability that has nothing to do with liquid water. Titan is a looking-glass world, a place where the rules of Earth are rewritten with a different set of ingredients. It possesses the only substantial, planet-like atmosphere of any moon in our solar system, a shroud so thick and complex it creates an environment eerily familiar and profoundly strange. This atmosphere is not a thin veneer but a dense, active entity, composed primarily of nitrogen like our own, but with a crucial difference. Where Earth's air is laced with oxygen and water vapor, Titan's is rich in methane and other hydrocarbons. This chemical shift changes everything. The pressure at Titan's surface is actually about 50% higher than the pressure at sea level on Earth. If you could stand there, you would not need a pressure suit to keep your body from exploding. You would need one to protect you from the bitter cold of -180 degrees Celsius. At that temperature, water is frozen harder than granite, but methane, a simple compound of carbon and hydrogen, takes on the role that water plays on our world. Titan has a complete, active hydrological cycle, but it is a hydrocarbon cycle. Methane evaporates from lakes, forms clouds in the yellow sky, and falls back to the surface as rain. That rain carves intricate river valleys through water-ice bedrock. It fills vast, dark lakes and seas in the polar regions, some larger than North America's Great Lakes. The shorelines are not sandy, but likely coated in tarry, organic compounds. Winds sculpt vast dune fields not of silica sand, but of plastic-like hydrocarbon grains stretching across equatorial deserts. We have seen it all through the eyes of the Cassini spacecraft and the Huygens lander, which sent back images of a pebble-strewn riverbed on a world a billion miles away. This is a landscape shaped by an active atmosphere, a world with weather, erosion, and seasons, but built from the chemistry of a deep freeze. The atmosphere itself is a factory for prebiotic molecules. High in the sky, sunlight and energetic particles break apart methane and nitrogen, allowing the fragments to recombine into ever more complex organic compounds, substances like ethane, propane, and even the building blocks of amino acids. These molecules slowly drift down, coating the surface in a thick layer of organic sludge. It is a continuous, planet-wide experiment in organic chemistry, the kind of process that on early Earth may have set the stage for life. And beneath this active, chemical sky lies perhaps the most tantalizing possibility. Data from Cassini strongly suggests that Titan harbors a global subsurface ocean of liquid water, a vast sea trapped between a shell of surface ice and a rocky core. This means Titan presents two radically different potential habitats in one package. On the surface, a bizarre, hydrocarbon-based environment rich in the organic ingredients for life, though far too cold for water-based biology as we know it. And deep below, in the dark, warm embrace of that hidden ocean, conditions could be much more familiar, a watery realm possibly heated by tidal forces from Saturn's immense gravity, where life might have found a way. Titan forces us to expand our definition of a habitable world. It is not in the Sun's traditional Goldilocks zone. It is far too cold for liquid water on its surface. Yet its atmosphere, that thick, insulating, chemically rich blanket, creates its own version of a habitable environment. It provides the pressure, drives the cycles, and manufactures the complex chemistry that could, in some form we have yet to imagine, support a genesis. A world becomes habitable not by matching our checklist, but by using its atmosphere to write its own rules. The raw materials for a sky are not born with a planet, they are delivered, and they must be set free. Before a world can have a climate, it must have an air, and the story of where that air comes from is a tale of cosmic bombardment and planetary breath. In the earliest days of a solar system, a newborn rocky planet may briefly hold what scientists call a primary atmosphere. This is a thick, primordial shroud captured directly from the swirling hydrogen and helium of the protoplanetary disk itself. But for a small world orbiting close to its star, this first sky is almost always a fleeting possession. The intense heat and radiation from the young star, combined with the planet's own modest gravity, quickly strips this lightweight envelope away, leaving behind a bare, molten sphere. The true, lasting atmosphere, the one that can define a world's character for billions of years, must be built from scratch. This is the secondary atmosphere, and its construction requires two key processes: delivery and outgassing. Imagine the early solar system as a chaotic construction site, with countless smaller bodies, planetesimals, comets, and asteroids still zipping around. Many of these objects are rich in what planetary scientists call volatiles, substances that easily vaporize like water, carbon dioxide, nitrogen, and methane. When these icy or carbon-rich impactors crash into the growing planet, they deliver their precious cargo. This violent rain is thought to be the primary source of Earth's oceans and much of the original gases in its air. But delivery is only the first act. To build a persistent atmosphere, the planet itself must learn to breathe. This breath is called outgassing. As the planet's interior cools and differentiates, with heavier elements sinking to the core and lighter ones rising, immense heat and pressure build within. This drives volcanic activity on a global scale. Molten rock or magma rising from the mantle contains dissolved gases, the same volatiles that were delivered by impacts now trapped within the planet's own body. When this magma reaches the surface through volcanoes or fissures, the pressure drops and the gases escape in great plumes, a process literally called degassing. The steam from a volcanic eruption is not just water from the surface. It is ancient water, primordial hydrogen and oxygen that have been stewing in the planetary interior for eons, now exhaled into the new sky. This is how a planet populates its own atmosphere. Carbon dioxide, water vapor, sulfur dioxide, and nitrogen are all common volcanic gifts. Without this geological respiration, a world might receive a temporary atmosphere from impacts, but it would have no way to replenish it as it slowly leaks to space or gets locked into rocks. This is why a geologically active interior is not just an interesting feature, it is the beating heart of atmospheric sustainability. A planet with a cold, dead interior like our Moon or Mercury has no volcanic outgassing. Any atmosphere it gains is temporary, destined to be lost. A world with ongoing geological activity, like Earth or even Venus, maintains a pipeline from its hot interior to its sky. This connection creates a long-term conversation. The atmosphere interacts with the surface, weathering rocks and forming oceans, while the interior continues to supply fresh volatiles, replacing what is lost and regulating the chemical balance over astronomical timescales. It is this deep planetary metabolism that allows an atmosphere to persist as a living, changing entity, rather than fading into a silent, airless memory. An atmosphere is a living chronicle, not a fixed portrait. The sky you see above you today is merely the latest page in a story billions of years long, a narrative of chemical revolution and cosmic chance. For a rocky world like Earth, this story follows a general yet deeply consequential sequence, a planetary coming-of-age tale where each chapter can lead to radically different futures. It begins in fire and chaos. After the primordial hydrogen and helium are stripped away, the young, molten planet starts to breathe. Intense volcanic activity, a process called outgassing, fills the new sky with gases from the seething interior. This creates a secondary atmosphere, typically thick and dominated by carbon dioxide, with traces of water vapor, nitrogen, and sulfur compounds. It is a toxic, high-pressure shroud, utterly hostile to life as we know it, but it is the essential raw material from which everything else is built. The next critical step depends entirely on temperature. If the planet orbits at a distance where it can cool sufficiently, that water vapor will eventually condense. It will fall from the sky in torrential rains that last for millennia, gathering in low basins to form the first global oceans. This moment is a planetary crossroads. The presence of vast liquid water begins to interact with the thick carbon dioxide atmosphere, starting to dissolve it and lock it away in carbonate rocks, a slow but powerful process that can moderate the intense greenhouse effect. This sets the stage for stability, but the most dramatic rewrite of the atmospheric script comes not from geology or physics, but from biology. On our world, once simple life emerged in those ancient seas, it began to manipulate its environment on a global scale. The advent of photosynthesis, the ability to harness sunlight to create food, had a planet-altering side effect, the release of oxygen as waste. For over 2 billion years, this oxygen was a deadly pollutant, rusting the oceans and driving ancient life forms to extinction. But gradually, it accumulated, transforming the air from a reducing, methane-rich haze into an oxidizing, nitrogen-oxygen mix. This great oxidation event was the single most profound change in Earth's atmospheric history, a chemical revolution authored by life itself that ultimately enabled complex, energetic organisms like us to breathe. Now follow this sequence down its other possible branches. Venus likely experienced the early chapters, the outgassing, and perhaps even the condensation of early oceans. But a subtle difference in solar heating, a lack of a stabilizing water cycle, or the absence of plate tectonics to recycle carbon, pushed it onto a different path. The carbon dioxide was never drawn down. Instead, a runaway greenhouse effect took hold, boiling away any oceans and leaving behind the permanent, scorching carbon dioxide blanket we see today. Its atmosphere evolved into a state of eternal, overheated youth. Mars tells a story of premature aging. It too had outgassing early oceans and possibly even a thicker, warmer carbon dioxide atmosphere. But its smaller size meant its internal engine cooled too quickly. Volcanic outgassing slowed, and the loss of its protective magnetic field left its atmosphere exposed to the solar wind. Instead of transforming biologically, its air was slowly, irrevocably stripped away, leaving a thin, frozen remnant. Its atmosphere evolved not into a new state but toward silence. These three siblings, born from similar materials, showcase the branching paths of atmospheric evolution. One became a stabilized, biologically altered world. One succumbed to a runaway chemical process. One faded away through physical loss. This reveals the core truth: a planet's habitability is not a permanent address. It is a chapter, a potentially fleeting condition in the long biography of its sky. For a world to be alive today, its atmosphere had to navigate eons of cosmic hazards, internal changes, and biological upheavals without tipping into irreversible catastrophe. The air we breathe is a historical document, a testament to a survival story 4 billion years in the making. The chemical story written in a planet's sky is not locked away. It is broadcast across the cosmos as light. For worlds orbiting distant stars, light is our only messenger, and we have learned to read its hidden language to taste the air of alien suns. When a distant exoplanet passes directly between its star and our telescopes, an event called a transit, it does more than cause a tiny dip in the star's brightness. If the planet has an atmosphere, a thin ring of that air is backlit by the star's intense glare. As the starlight filters through this gaseous halo, specific colors or wavelengths are absorbed by the molecules present. This method, transmission spectroscopy, is like holding the planet up to a brilliant light and seeing the unique fingerprint its atmosphere leaves on the spectrum. Each molecule has a barcode, a set of dark absorption lines where it has stolen a piece of the light. Water vapor, methane, carbon dioxide, even sodium, all leave their distinctive marks. By carefully dissecting this filtered starlight, astronomers can deduce the chemical composition of an atmosphere tens or hundreds of light years away. For larger, hotter worlds, we can also use direct emission spectroscopy. When a planet orbits its star, we can sometimes isolate the tiny amount of infrared light it emits from the overwhelming glare of its sun. The heat radiation coming from the planet's own atmosphere also carries spectral signatures. By analyzing this glow, we can map temperature gradients, detect high-altitude clouds, and identify molecules that might be less visible in transmission. These remote sensing techniques transform a distant point of light into a complex chemical portrait. We are no longer just detecting a planet's existence, we are beginning to analyze its breath. The discovery of water vapor in the atmosphere of a temperate, rocky exoplanet would be a monumental event. Finding methane alongside oxygen would send shockwaves through the scientific community, as that combination strongly suggests a continuous biological source. Detecting a thick haze of photochemical smog like on Titan would tell us of a world with active, complex atmospheric chemistry, even if it lies far outside the traditional habitable zone. This is how we move beyond the simple checklist of orbital distance. We are learning to assess a world's true potential not by where it is, but by what it is made of. The presence of an atmosphere itself is the first great filter, and its composition is the second. These faint spectral lines are our only clues to answering the ultimate question. Is that distant blue dot merely a rock in space, or is it a world wrapped in a transformative and perhaps even living sky? But a chemical signature in the sky is not a confession. It is a clue, and in the cosmic detective story of finding life, clues can be misleading. The ultimate goal in reading the light from an exoplanet's atmosphere is to find a biosignature, a combination of gases so out of chemical equilibrium that it strongly suggests something is actively, relentlessly producing them. On Earth, the classic example is the coexistence of oxygen and methane. In our atmosphere, these two gases are like fire and fuel. They desperately want to react with each other and disappear. The fact that we have significant amounts of both means something is constantly pumping them into the air faster than chemistry can remove them. For oxygen, that something is photosynthesis. For methane, it's a mix of biological sources like microbes in wetlands and geological activity. Finding this pair in another world's air would be one of the most exciting discoveries imaginable. Other potential biosignatures include nitrous oxide, produced by microbes in soil and oceans, or certain ratios of gases that simply don't make sense under normal planetary conditions. Yet, the universe is a master of mimicry. For every true biosignature, there exists a false positive, a purely geological or chemical process that can create the same atmospheric pattern without a single living cell involved. Take oxygen, the gas we most associate with life. A lifeless world can build up an oxygen atmosphere through simple physics. On a planet orbiting a cool red dwarf star, intense ultraviolet radiation can break apart water vapor or carbon dioxide molecules high in the atmosphere, a process called photolysis. The lightweight hydrogen from broken water can then escape to space, leaving behind a buildup of leftover oxygen. Over billions of years, this abiotic process could fill an airless world with a substantial oxygen atmosphere, a cruel mirage for distant observers. Similarly, methane can be produced without biology. A geological process called serpentinization occurs when water reacts with certain types of iron-rich rocks, like olivine, deep underground. This reaction produces hydrogen, which can then combine with carbon to form methane, which vents to the surface through hydrothermal systems. We see this happening on Saturn's moon Enceladus and likely on Mars. A methane-rich atmosphere, therefore, could just be the sign of a geologically active water rock world, not a living one. This means a single gas in isolation is almost meaningless. Context is the only true decoder. To have confidence in a potential biosignature, we need to understand the entire planetary system. We must ask, what kind of star does it orbit? A quiet, mature star like our Sun makes biological oxygen more plausible, while a violent young star makes abiotic oxygen production more likely. What is the planet's climate? Is it temperate or so hot that all water has been lost to space, making biological processes impossible? Most critically, what is the geological context? Does the planet show signs of active volcanism and plate tectonics that could supply non-biological methane or alter gas ratios? A true assessment requires piecing together a holistic portrait, ruling out every known non-biological explanation before daring to whisper the word life. It is a process of elimination on a cosmic scale. The discovery of a potential biosignature will not be a single eureka moment, but a long, cautious argument built from multiple lines of evidence, a case we must make to the universe itself. So what does the perfect sky for life look like? By weaving together everything we've explored, we can now define the concept of a habitable atmosphere. It's the specific set of atmospheric conditions that could allow a world to cradle life as we know it on its surface. First, it must have sufficient atmospheric pressure, a sky with enough weight to hold liquid water stable, preventing it from instantly boiling away or only existing as permanent ice. Second, it requires a temperate greenhouse effect, one strong enough to raise global temperatures above freezing, but not so intense that it triggers a runaway disaster like on Venus. This delicate balance creates the stable, moderate temperature range where complex chemistry can thrive. Third, the atmosphere must offer protective shielding, filtering out harmful stellar radiation and incinerating smaller meteoroids before they can bombard the surface. Fourth, and perhaps most critically, the climate must be stable over geological timescales. This demands the presence of negative feedback loops, like the Carbonate-Silicate Cycle, that automatically correct for changes and prevent wild swings between global ice ages and scorching heat waves. Finally, the bulk composition of the air must be non-toxic to Earth-like life, with reactive gases like oxygen carefully balanced by stable buffers like nitrogen, avoiding a corrosive or suffocating chemical environment. This list is, of course, profoundly Earth-centric. It describes the very specific conditions that allowed our own story to unfold. The universe is undoubtedly more inventive, and life may find ways in environments we cannot yet conceive, like the hydrocarbon seas of Titan or the subsurface oceans of icy moons. But this framework gives us a concrete, evidence-based starting point. When we point our telescopes at distant exoplanets and begin to analyze their light, these are the criteria we use to separate the merely interesting from the truly promising. They help us identify which worlds, among the thousands, have wrapped themselves in that rare and precious combination of blanket, shield, and sustainer, a sky that doesn't just exist, but actively nurtures the possibility of a living surface. Without an atmosphere, a world is simply a rock in space. To understand the transformative power of a sky, we must first look at its absence, at the silent, stark baseline of barrenness. Consider Mercury, the innermost planet. Its surface is a scorched and cratered landscape where daytime temperatures soar high enough to melt lead, while the endless night on its dark side plunges to a cold that would freeze air itself solid. This 1,000-degree swing happens because there is no atmospheric blanket to moderate the sun's fury or to trap any lingering warmth. The heat it receives during its long day radiates unimpeded back into the void the moment that spot rotates into darkness. The moon tells a similar story. Its gray, dusty plains are a museum of impacts, preserving every crater from billions of years of bombardment because there is no air to burn up smaller meteoroids, no wind or rain to slowly erase the scars. Walking on its surface, an astronaut's footprint will remain pristine for millennia, untouched by any form of erosion. These are static worlds, their surfaces shaped only by the sudden, violent punctuation of asteroid strikes and the slow, relentless grinding of solar radiation. They have no weather, no seasons, no gentle chemical interaction between rock and air. Their surfaces are directly exposed to the full spectrum of stellar radiation and a constant drizzle of micrometeoritic dust. This is the fate of any rocky body too small to hold onto an envelope of gas, or whose internal geological engine has gone cold, ceasing to replenish what was lost. They become inert, their stories written entirely in the geometry of impact craters and the chemistry of untouched rock. This profound stillness is the cosmic default. It shows us that the vibrant, changing planet we call home is the extraordinary exception. An atmosphere is not a minor accessory. It is the fundamental catalyst that turns a passive piece of orbiting geology into an active, evolving world. It is the difference between a silent stone and a planet that can whisper, with wind and rain, the possibility of something more. The ultimate test of our atmospheric understanding may not be reading the skies of other worlds, but writing them ourselves. This is the speculative science of terraforming, the deliberate planetary scale engineering of an environment to make it habitable for Earth-like life. It is a concept that transforms a planet from a place we visit into a place we could one day call home. The most compelling candidate for this thought experiment is Mars, a world whose story of atmospheric loss we have already traced. To reverse that loss, to gift Mars a new sky, would be to attempt the most ambitious project in human history. The first and most critical step would be to thicken its atmosphere, to rebuild the pressure blanket that vanished billions of years ago. The raw materials are already there, locked away. Vast reserves of carbon dioxide are frozen into the polar ice caps and bound within the Martian soil. One theoretical approach involves using orbital mirrors to focus sunlight on the poles, or spreading dark dust to absorb more heat, triggering a controlled release of this frozen CO2. As the gas enters the thin air, it would begin a self-reinforcing cycle. Carbon dioxide is a greenhouse gas. Its increasing presence would trap more of the sun's weak heat, warming the planet further. This warming would then release even more CO2 from the soil and ice, thickening the atmosphere and strengthening the greenhouse effect in a cascading process. The goal of this initial phase would not be a breathable atmosphere, but a thicker, warmer one. Surface pressures might rise from less than 1% of Earth's to perhaps 5 or 10%, still far too thin for us to breathe without assistance, but potentially sufficient to allow liquid water to exist in stable pools during the warmest part of the Martian day. To accelerate the warming, we might need to manufacture and release synthetic super greenhouse gases, compounds designed to be thousands of times more effective at trapping heat than carbon dioxide. These could be produced on-site from Martian resources and released into the budding atmosphere, acting as a planetary thermostat to push temperatures steadily upward. If this great warming succeeded, the next, far more difficult chapter would begin: the transformation of the air's chemistry. A thick, warm carbon dioxide atmosphere is a start, but for humans to walk freely, we would need oxygen. This requires biology. We would need to introduce engineered, hardy microorganisms, likely extremophiles from Earth or synthetically designed variants, that could survive in the still harsh Martian conditions. Their mission would be photosynthesis, using the abundant sunlight and carbon dioxide to produce oxygen as a byproduct, just as early cyanobacteria did on Earth. This process would not be measured in years or even centuries, but in millennia. The great oxidation event on our own planet took over 1 billion years to fill the sky. Even with advanced bioengineering, creating a breathable oxygen level on Mars could easily take tens of thousands of years of careful stewardship. The technological hurdles are beyond our current imagination, requiring self-replicating robotic factories, global genetic engineering projects, and a level of planetary systems management we can scarcely conceive. And this leads to the profound ethical questions. Do we have the right to fundamentally alter another world, especially one that may harbor its own undiscovered microbial life in subsurface niches? Would we be gardeners or conquerors? The process itself would be irreversible on human timescales, a permanent commitment etched into the geology and sky of another planet. Terraforming is not a near-future blueprint, it is a mirror. It forces us to apply every principle of atmospheric science we have learned, from greenhouse physics and pressure thresholds to chemical cycling and climatic stability, and ask if we could deliberately rebuild that majestic, delicate system. It frames our entire understanding of habitable skies not just as knowledge, but as a potential tool, challenging us to consider whether we might one day graduate from reading the stories of atmospheres to writing entirely new ones. The most extreme test for a planetary atmosphere is a world that never turns. Around the faint, red dwarf stars that make up most of our galaxy, the most common place to find a rocky planet in the temperate zone is perilously close to its dim sun. At such intimate distances, gravity takes a firm hold, forcing the planet into a state called tidal locking. One hemisphere faces the star in permanent, blazing daylight. The other is cast into an endless frozen night. By the simple logic of sunlight alone, this should be the end of the story. A world split into two halves of hell, with no place for liquid water or life. But a planet's atmosphere can rewrite this fatal sentence. If the world is massive enough to hold onto a thick, global blanket of air, that atmosphere becomes a heroic heat transport system. The physics are driven by staggering inequality. The dayside, under constant stellar fury, becomes intensely hot. The air there heats up, expands, and rises violently. This creates a colossal zone of low pressure. Meanwhile, on the night side, the air cools, contracts, and sinks, creating a high-pressure zone. The atmosphere's relentless drive toward equilibrium sets up a planet-wide conveyor belt. Superheated air races high above the surface from the dayside toward the night side. As it travels into the darkness, it cools and eventually plummets toward the ground. Then, at the surface, a return flow of now cold air rushes back across the terminator toward the dayside low pressure, only to be heated and lifted again. This isn't just weather, it is a permanent, howling storm engineered by the planet's very rotation or lack of it. The result could be a world where the habitable region is not a band of latitude, but a delicate ring of twilight. Along the Terminator line, the border between eternal day and eternal night, these raging atmospheric currents might mix just enough warmth from the day side with just enough coolness from the night side to create a narrow, temperate zone. Here, temperatures could potentially allow liquid water to exist. It would be a strange and precarious habitat. The sun would never rise or set. It would hang motionless on the horizon, a permanent fixture of either dawn or dusk depending on which side of the line you stood. The sky would likely be dominated by fierce, unending winds as the atmosphere labored to balance the stars' uneven gaze. Clouds might perpetually gather along this twilight ring, feeding from evaporation on the hot side and precipitating as they cooled over the dark side. This scenario forces a dramatic expansion of the classic habitable zone concept. A tidally locked planet is, by orbital position alone, a terrible candidate for life. Its day side is far too hot, its night side far too cold. Yet, through the dynamic power of a thick, circulating atmosphere, it can manufacture its own pocket of possibility right at the seam between light and dark. Habitability here is not gifted by orbital geometry. It is earned through atmospheric motion. The very existence of such a terminator zone depends entirely on the atmosphere's ability to move heat with enough vigor to prevent the night-side gases from freezing solid and collapsing onto the surface, and to keep the dayside from overheating into a permanent, incinerating inferno. It is a testament to the atmosphere's role not as a passive blanket, but as an active global engineer, capable of carving out a niche for survival in the most unlikely of places. This reveals a universe where the potential for life may not always lie under a friendly, moving sun, but could persist in the eternal, wind-swept twilight of a world that forever faces its star. While a runaway greenhouse effect can boil a world's oceans, the opposite catastrophe is just as chilling. A planet can freeze itself solid, locking every ocean under a global shell of ice in a state scientists call a Snowball Earth. This is the nightmare of a runaway icehouse, where the same atmosphere that gives warmth becomes an accomplice in a planet's deep freeze. The trigger can be subtle, a slight dip in solar output, a change in planetary tilt or orbit, or a temporary drop in greenhouse gases. As the planet cools, ice begins to advance from the poles. This is where a powerful positive feedback takes hold, the ice-albedo effect. Fresh ice and snow are brilliantly white, reflecting most sunlight back into space. As more ice forms, the planet reflects more energy, which causes more cooling, which leads to more ice. This self-reinforcing loop can spiral out of control, the ice sheets marching relentlessly toward the equator until they meet, encasing the entire world in a single, glittering ice sphere. The oceans, perhaps a kilometer deep in ice, and the continents, buried under glaciers, would become a global desert of cold. Temperatures could plummet to -50 degrees Celsius globally. From space, the planet would shine with a blinding, white glare, a silent snowball adrift in the void. This is not just a theoretical horror story. Evidence written in ancient rocks suggests our own Earth may have experienced these profound freezes at least twice, over 600 million years ago. The planet we know as a blue marble may have twice become a white marble, its vibrant biosphere driven to the brink. Life at the time, consisting mostly of single-celled organisms in the oceans, would have been trapped in a desperate struggle for survival. The global ice cover would have drastically reduced the sunlight reaching the liquid water below, choking off the energy for photosynthesis. The ice would have also sealed off the ocean from the atmosphere, preventing the normal exchange of gases. It is a scenario that seems like a permanent end, a planet locked in an icy tomb from which there is no return. Yet Earth thawed, the ice receded, and life not only survived but exploded in diversity shortly after these events. How is such an escape possible? The answer, once again, lies in the patient, relentless breath of the planet itself. Beneath that global carapace of ice, the planetary engine kept running. Volcanoes continued to erupt, piercing through the ice on continents and perhaps even on the seafloor. These volcanoes performed a vital service, exhaling carbon dioxide into the air. With the oceans sealed by ice and most rock weathering halted by the frozen surface, there was no rain, no rivers, no mechanism to draw this carbon dioxide down and lock it into rocks. The greenhouse gas had nowhere to go. For millions of years, as the snowball state persisted, volcanic outgassing steadily, inexorably built up the carbon dioxide concentration in the atmosphere. It was a slow, invisible charge, a buildup of climatic potential energy. Eventually, the concentration reached a critical threshold. The greenhouse effect became so powerful that it could begin to overwhelm the brilliant reflectivity of all that ice. At the edges of the glaciers, perhaps in the tropics where sunlight was strongest even if reflected, a tiny amount of melting would begin. This exposed darker ocean water or land, which absorbed more heat, causing more melting, initiating a reverse feedback loop. The thaw, once it began, would have been geologically rapid and spectacularly violent. With a sky now thick with carbon dioxide, temperatures would have soared. The ice sheets would have collapsed, and the planet would have rocketed from a deep freeze into a super-hot, humid greenhouse world. Torrential rains would have returned, weathering the continents at a furious pace and finally drawing the excess carbon dioxide back down, eventually restoring a temperate balance. This epic cycle demonstrates the atmosphere's ultimate role as a planetary mediator between extremes. It is not just the cause of global catastrophe, it is also the mechanism of salvation. The same volcanic outgassing that can contribute to a runaway greenhouse on a world like Venus became, on a frozen Earth, the very key that unlocked the ice. It highlights the profound importance of that long-term geological conversation between a planet's interior and its sky. A world without active volcanism, if it ever fell into a snowball state, might remain frozen forever, its atmospheric blanket too thin to ever muster the warmth for an escape. Earth's episodes show that habitability is a dynamic, contested state, a balance maintained over eons by forces far greater than any single event. The atmosphere is both the blanket that can be stolen, plunging a world into cold silence, and the patient, breathing force that can, given enough time, stitch that blanket back together again. Our own star holds a secret from its youth, a puzzle written in ancient rock and distant starlight. Models of solar evolution reveal a surprising fact. The infant sun was significantly dimmer than it is today, shining with only about 70% of its current warmth. By the straightforward math of sunlight alone, a planet like Earth, orbiting at our distance, should have been a frozen snowball for its first 2 billion years. Its oceans should have been locked under a global sheet of ice, a world inhospitable to the very origins of life we know began during that time. Yet, the geological record tells a completely different story. Some of the oldest rocks on our planet, formations over 3.8 billion years old, bear the unmistakable signatures of liquid water, ripple marks from ancient streams and minerals that can only form in a wet environment. This glaring contradiction is known as the faint young sun paradox. How could Earth have been warm enough for flowing water when its primary source of heat was so much weaker? The solution lies not in the star but in the sky it shone upon. To compensate for that fainter sun, Earth must have wrapped itself in a much thicker atmospheric blanket, one supercharged with greenhouse gases. The leading candidate is carbon dioxide. In our planet's fiery infancy, volcanic outgassing would have vented enormous quantities of carbon dioxide into the air. Without widespread oceans or continents to immediately begin the weathering process that locks carbon away in rocks, this gas could have built up to concentrations tens or even hundreds of times higher than today's levels. This dense carbon dioxide shroud would have created an intense greenhouse effect, trapping enough of the sun's meager heat to raise global temperatures above freezing. Some scientists also suggest that methane, an even more potent greenhouse gas produced by early microbial life or geological processes, may have played a supporting role, adding another layer to the insulating blanket. This ancient atmosphere was a far cry from our breathable modern air. It was a dense, hazy, and likely orange-tinted fog, a necessary cocoon of heat that kept the young planet from a permanent deep freeze. The faint young sun paradox teaches us a profound lesson about the longevity of habitable worlds. A planet's atmosphere cannot be static. It must be in a dynamic dialogue with its aging star. As our sun slowly grew brighter over billions of years, Earth's atmosphere had to evolve in the opposite direction. The gradual drawdown of carbon dioxide through the weathering of rocks and the burial of organic carbon carefully tuned the greenhouse effect, preventing our planet from overheating into a Venus-like state as solar intensity increased. This reveals a delicate balancing act that spans eons. Habitability is not a one-time condition granted by orbital position. It is a continuous achievement of atmospheric regulation. A world must possess not just an initial blanket, but the geological and perhaps biological processes to adjust that blanket's thickness over astronomical timescales. The paradox frames our own existence as the result of a 4-billion-year conversation between a warming star and a cooling sky, a conversation that had to be precisely timed. It makes us wonder how many other Earth-like worlds failed this test, freezing solid in their stars' dim youth or boiling away as their suns matured, simply because their atmospheres could not keep pace with the change. The atmosphere you stand beneath is not a permanent possession. It is a temporary loan from a planet's gravity and geology under constant siege from the void. The struggle to hold onto a sky is fought along several fronts, each with its own method of theft. The first and most basic is thermal escape, sometimes called Jean's escape. Picture the molecules in the air above you not as a placid gas but as a frantic swarm. Each particle zips around with a speed determined by the temperature. Lighter molecules like hydrogen and helium move the fastest. If a molecule at the top of the atmosphere reaches a speed greater than the planet's escape velocity, it can simply fly off into space, never to return. It is a slow, steady leak, most effective for the lightest gases on smaller, warmer worlds. This is why Earth cannot hold onto hydrogen or helium for long, and why a small, hot world like Mercury was stripped bare early on. But for a young planet orbiting a violent, young star, the escape can be far more dramatic. This is hydrodynamic escape, an extreme version of the thermal process. Imagine the upper atmosphere not as individual molecules leaking away, but as a river of gas boiling off the planet entirely. This happens when the star emits immense amounts of extreme ultraviolet radiation. That energy doesn't just heat the air, it superheats it, inflating the upper atmosphere to a puffy, extended state and giving whole layers of gas enough energy to flow outward like a solar wind, dragging even heavier gases with it. Many of the hot, rocky exoplanets we see orbiting close to their stars, known as lava worlds, may be in the throes of this atmospheric evaporation right now, their skies being blown away into a glowing, comet-like tail. Then there is the violence of catastrophe, impact erosion. In the early solar system, giant collisions were commonplace. When an asteroid or comet the size of a small moon strikes a planet, the energy released is almost beyond comprehension. The impact can blast a plume of vaporized rock and atmosphere high into space, and if the ejector reaches escape velocity, that chunk of the sky is simply gone. A single, sufficiently large impact can remove a significant percentage of a planet's atmosphere in an instant. It is believed that the impact that created our moon may have also stripped away any primordial atmosphere Earth had at the time, forcing our planet to start over with a secondary atmosphere from volcanic outgassing. For a world like Mars, however, the most insidious thief has been non-thermal escape. Without a global magnetic field to act as a shield, the Martian atmosphere lies exposed to the solar wind, that relentless stream of charged particles from the sun. One key process here is sputtering. When high-energy ions from the solar wind slam into molecules in the upper atmosphere, they can knock those molecules loose like billiard balls, sending them on trajectories that escape Mars's gravity. Another is photochemical escape. High-energy solar ultraviolet radiation breaks apart molecules like carbon dioxide or water vapor high above the planet. This creates lightweight atoms like oxygen that are given a strong kick of energy from the breakup itself. That extra energy can be enough to send them fleeing into space. NASA MAVEN orbiter has watched this happen at Mars in real time, measuring how solar storms dramatically increase the rate of atmospheric loss. Over billions of years, this slow, relentless scouring by the solar wind is believed to be a primary reason the red planet's once thick sky is now just a faint remnant. These mechanisms reveal a fundamental truth. A planet's atmosphere exists in a state of dynamic tension. It is continually replenished from below by geological activity and continually stripped away from above by stellar forces and cosmic accidents. For a world to maintain a stable, life-nurturing sky across eons, it must strike a delicate, ongoing balance between these opposing flows. The calm air we breathe is not a default condition of the universe. It is the hard-won prize of a planet that has successfully defended its sky moment by moment for billions of years. A planet's magnetic personality is its invisible shield. Deep within Earth's core, a churning dynamo of molten iron generates a powerful global magnetic field. This field extends far out into space, weaving a protective bubble called the magnetosphere. Think of it not as a solid wall, but as a vast, invisible force field that surrounds our entire world. Its primary role in the story of atmospheres is defense. It stands guard against the solar wind, that relentless stream of charged particles constantly blowing from the sun. Without this shield, those high-energy particles would strike the upper atmosphere directly, blasting molecules into space through a process called sputtering. Our magnetic field deflects the vast majority of this corrosive wind, channeling the particles safely around the planet and toward the poles, where they interact with gases to create the beautiful auroras. This protection drastically reduces non-thermal atmospheric escape, the kind of slow, insidious stripping that does not rely on heat. It is a guardian that allows our atmosphere to persist relatively untouched across billions of years. Now look at the stark contrast next door. Mars once likely had a similar molten core and a global magnetic field, but being a smaller world, its interior cooled faster. That internal dynamo ceased and the protective field collapsed. What remained was a patchwork of weak, fossilized magnetism locked in ancient rocks, but no planetary shield. Once exposed, Mars' atmosphere lay utterly vulnerable to the solar wind. Over eons, that relentless stream scoured away the air, molecule by molecule, contributing profoundly to the planet's transition from a wet world to a dry, frozen desert. The loss of its magnetic field was not the sole cause, but it was a critical turning point, removing a key defense just when the atmosphere needed it most. Venus presents a fascinating middle ground. It has no global intrinsic magnetic field generated by a core dynamo like Earth's. Its core may not churn in the right way, or it may have simply stalled. Yet Venus holds an atmosphere 90 times thicker than our own. How does it manage this without a magnetic shield? The answer is sheer mass and gravity. Venus is nearly Earth's twin in size, and its gravitational grip is so strong that even without magnetic protection, the rate of atmospheric loss to the solar wind is relatively slow. Furthermore, Venus has developed a different kind of defense, an induced magnetosphere. The solar wind itself, interacting with the planet's thick ionosphere, the charged upper layer of its atmosphere, creates a magnetic barrier that provides some deflection. It's a makeshift shield generated from the outside in rather than the inside out, but it offers a degree of protection. So, is a magnetic field an absolute requirement for a world to keep its air? Venus proves it is not. A massive planet with intense gravity can retain a thick atmosphere through brute force alone. But for long-term habitability, especially for a world like Earth that relies on a thinner, more balanced atmosphere, a global magnetic field is a major protective asset. It is a stabilizing force that dramatically slows atmospheric erosion, buying precious time for geological and biological processes to regulate the climate. It helps preserve the delicate pressure and chemical balance that liquid water and life require. In the grand billion-year biography of a planet, a magnetic field is not just a feature, it is a sustained act of planetary self-defense, a silent guardian ensuring that the story written in the sky does not simply fade away into the silent dark. But a world's potential for life is not written only on its surface. Some of the most promising habitats in our solar system exist in perpetual darkness, locked away beneath a frozen crust. Moons like Jupiter's Europa and Saturn's Enceladus present a radical alternative to the classic model of habitability. They possess no substantial surface atmosphere to speak of, no global blanket to trap heat or shield against radiation. Their faces are icy, airless, and scarred by cracks. Yet, beneath that forbidding exterior, evidence strongly suggests they harbor vast, global oceans of liquid water, kept warm not by sunlight, but by the relentless gravitational kneading of their giant parent planets. This tidal heating creates a hidden, watery realm entirely separate from the sky above. The connection to atmospheric science here is subtle but profound. While these worlds lack a traditional sky, they are not entirely silent. Europa has a wispy, tenuous atmosphere of oxygen, not from life, but from the violent bombardment of its ice surface by Jupiter's intense radiation. The radiation splits apart water molecules, and the lightweight hydrogen escapes, leaving behind traces of oxygen. More intriguing are the giant plumes of water vapor and ice crystals that spacecraft have observed jetting into space from Enceladus's south pole. These are not weather systems, they are direct geysers, violent vents connecting the hidden ocean below to the vacuum above. The plumes contain not just water, but a cocktail of salts, organic compounds, and molecular hydrogen. They are a sample, delivered free of charge, of the chemistry occurring in that sunless sea. This forces us to ask a fascinating question. Could a thriving biosphere, entirely hidden beneath kilometers of ice, ever announce its presence to the universe? Could life in a subsurface ocean produce a detectable atmospheric signature? The possibility, while challenging, is not zero. Microbial life in that dark ocean would engage in metabolism, consuming nutrients and producing waste gases. Some of those gases, like methane or certain sulfur compounds, could be carried upward by geological circulation. If they reach the ocean floor, they might enter hydrothermal systems and get injected into the plumes, venting directly into space. A future telescope analyzing the faint spray from such a plume might one day detect an anomalous concentration of a gas that is hard to explain by geology alone. The biosignature would not be in a global, stable atmosphere, but in a fleeting, localized geyser cloud, a whisper from the deep, caught for a moment in the sunlight before dispersing into the void. This expands the very framework of atmospheric science. It shows that the study of a world's air, or even its lack thereof, is inseparable from the story of its interior. For these icy moons, the atmosphere is not a nurturing blanket, but a fleeting message, a faint exhalation from a hidden ocean. It connects the deep, internal chemistry of a world to the cosmic arena, proving that even a seemingly airless ball of ice can participate in the grand conversation of planetary transformation, speaking volumes through what little it chooses or is forced to exhale. This journey from barren rock to living world is not a single event, but a precise and perilous sequence. It begins with a planet of sufficient size and internal fire, a world massive enough to hold onto its gases and geologically active enough to exhale them. From that volcanic breath, a secondary atmosphere is born, a thick and turbulent shroud. But that is only the raw material. For transformation to begin, that atmosphere must possess a very specific set of properties. Its composition must include greenhouse gases like carbon dioxide or methane in just the right amount to act as a planetary thermostat, trapping enough starlight to create a temperate range. Its pressure must be high enough to act as a lid, holding liquid water stable on the surface instead of letting it boil away or remain forever frozen. It must also be a guardian, rich enough to burn up incoming space debris, and ideally partnered with a magnetic field to deflect the stellar wind that would otherwise slowly strip the sky away. Yet even with all this, a world is not yet secure. The final, and perhaps most rare, requirement is long-term stability. The atmosphere must be part of a grand, self-regulating conversation with the planet's surface and oceans. It needs feedback loops like the slow dance of the Carbonate-Silicate Cycle that can correct for changes over millions of years, preventing a slide into either a global icehouse or a runaway greenhouse. Each of these steps is a filter, a narrow gate that a world must pass through. A planet can be the right size but too cold inside, losing its geological voice. It can have a thick blanket but one of the wrong chemistry, creating a toxic or inert environment. It can have a temperate climate for a short epoch, only to see it unravel because it lacks the geological machinery for balance. The journey from an ordinary, silent rock to a world humming with the possibility of life requires this exquisite confluence of factors, each dependent on the last. Our own blue marble, with its gentle pressure, its balanced greenhouse, its protective shields, and its ancient stabilizing cycles, represents not the common outcome of planetary formation, but a spectacularly fortunate alignment. The air we breathe is the product of a billion-year symphony where gravity, geology, chemistry, and even biology had to play in perfect time. It is a phenomenon of breathtaking rarity, a transformative cloak that turns the cold silence of space into a whisper of home. The search for another Earth, then, is not a hunt for the right orbit alone. It is a search for the right sky. An atmosphere is the ultimate planetary architect, a dynamic force that sculpts a world's destiny from raw materials of gas and light. It is the climate controller, setting the thermostat through the delicate balance of the greenhouse effect. It is the protective shield, filtering lethal radiation and weathering the endless rain of cosmic debris. And it is a chemical factory, brewing the complex molecules that can become the precursors to life itself. This perspective fundamentally reshapes how we look out into the galaxy. Finding a rocky planet in the habitable zone is only the first, faint clue. The real investigation begins when we train our telescopes not on the planet's shadow, but on the thin ring of starlight filtering through its air. Atmospheric characterization is the new frontier. It transforms a distant dot of light into a world with weather, with chemistry, with a story. This is the core task for the next generation of observatories, like the James Webb Space Telescope and the Future Habitable Worlds Observatory. These instruments are not just bigger eyes, they are sophisticated chemical analyzers designed to read the spectral fingerprints of alien skies. They will test every principle we have explored, applying them to not just one or two promising worlds, but to thousands. We will see planets with carbon dioxide atmospheres undergoing runaway greenhouses, and others where that same gas maintains a temperate balance. We may find worlds shrouded in Titan-like organic hazes, and perhaps one day, a world whose air holds that elusive, unstable combination of gases that whispers of a biosphere at work. Each new spectrum will be a chapter in a grand comparative planetary science, teaching us which atmospheric recipes are common and which are vanishingly rare. This incredible leap in understanding also turns our gaze back home, casting our own blue sky in a new and precious light. The gentle pressure that lets rain fall, the transparent window that bathes us in safe sunlight, the intricate cycles that have maintained a stable climate for eons, these are not cosmic defaults. They are the fragile, hard-won achievements of a specific planetary history. Our atmosphere is more than the air we breathe. It is the living, breathing system that has written the entire story of life on this world. As we prepare to read the stories of other skies, let that deepen our wonder for the transformative and extraordinarily rare envelope that makes our own world anything but ordinary.